Okay, so in this chapter, we talk about circuits, or more specifically, the linear circuit, actually the RL circuit, RLC circuit. But in this chapter, we'll limit the circuit for lower than first order, or I should say, not more than first order, maybe zero order. So let's start. So first, we'll talk about the single loop circuit, which is very, very easy. And then the multi-loop circuits, we will apply the Kirchhoff current law and Kirchhoff voltage law to try to solve the circuit. Actually, we'll start from purely resistive circuit, which is zero order. And then we'll talk about the ampere meter, voltage meter, and finally we'll talk about the RC circuits, which is a type of first order circuit. So single loop circuit, to produce a static flow of charge, you need a charge pump. So this is the charge pump, which a device that by doing work on charge carriers maintain a potential difference between a pair of terminals, or blah 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 blah. But actually you can simply regard it as a battery, but in this book it call it the EMF device. The long form is electromotive force device. So consider, actually you can consider it to be a battery, AA battery, AAA battery, something like that. So there's a part of simple circuit to provide a voltage between, maybe you can just regard this is this is the ground of your circuit, and then there is a voltage. Usually in double E sense, we used to use V rather than E, but in this textbooks it uses E for the EMF, or the battery. But actually it's the same thing. And this circuit is pretty simple. It consists of only a battery and also a resistor R. The EMF device keep one terminal positive, so you need to determine this is positive, this is negative, or in a battery, something like this. So this is positive, this is negative. I suppose all of you should have seen an AA battery. And so we can represent the EMF of the device with an arrow that point from the negative terminal. So it uses this arrow to demonstrate the polarity of this battery. And this is not really important in my opinion. And EMF device does not charge to maintain, does work on charge to maintain potential difference between the output terminals. So if work done, dF is the work the device does to force the positive charge from negative to positive terminal. Then the EMF of the device is something like this. So it has worked to move some positive charge to move from the negative side to this side. But as you know, actually this is electron. So On the contrary, you can regard it as some electron moving from the positive side to negative side and going this way. But if you consider this positive charge, it should be going that in another way. Because as the circuit theory developed, the electron has not been discovered. In chapter 28, you learn the Hall effect. They start to know that, oh, there should be the negative charge rather than positive charge. So next, an ideal EMF is one less and the internal resistance. So it's just a voltage. It's just a voltage difference between this point and that point. There are no resistance inside this or in series with it. So this is what we call an ideal EMF device. If it is a real EMF device, it has internal resistance, we can regard it as an ideal EMF in series with usually a small resistance. But as long as there are no current, then an ideal resistance and real real EMF device and real EMF device is you cannot distinguish between them, because there are no as long as there are no current going through it, then there is no voltage drop on the internal resistance. Then you cannot distinguish. So let's try to solve this the easiest circuit, single loop circuit. So in this textbook, it demonstrates the energy method. Actually, I seldom see this method in my opinion, as I have so many as I have read many circuit theory books. We seldom use the energy method, but I just presented to you. There is another method in physics perspective, in a physics point of view. So it's quite interesting. It is quite interesting, in my opinion. So, but actually, I will also demonstrate the potential method, which is a method that I am more familiar with it. I usually use the potential method rather than the energy method. So for the energy method, as we know, the power dissipation of a resistor is P equals to I squared R. And in the time interval delta dt, which is a very short time interval, the energy consumed by this R should be the power times the time, which is the work, which is the energy. And this energy is said to be dissipated by this resistor. And as we know that for the EMF, it done some work to move the charge, and the charge is actually IT. And I think in chapter 26, you know that Q equals IT, and or I equals dq dt. If I may not be uniform, But so I is the first derivative of the Q. I is the first derivative of Q. So we can write that dq is I dt. And then we know that in the previous slide, we know that dw is e dq. the EMF try to done some work, which is E, the voltage difference between this battery, the A and maybe B at this maybe B here. So this is the voltage difference between these two terminals, and then dq is the charge it tries to move. So we substitute dq equals to I dt here. So we have something like this. And actually, it done some work, and the work is consumed by this resistor, so that we can equate. We can let this one equals to this one equals to this one due to the conservation of energy. Due to the conservation of energy. The work done on the ideal battery must equal to the thermal energy. It cannot store some energy there because there's no place to store it. So as long as it done some work, all the work should be consumed by the resistor. So this one is equal to that one. So we can write like this, and dt can be cancelled. I square, one of it is cancelled. So finally we get I equals to VR, which is nothing but an Ohm's law. So that's why I said the form is actually the same as the Ohm's law, which you should have learned it in chapter 26. That's why the argument of this page is quite long, but it turns out to be a very simple conclusion, which is interesting. So let us consider the potential method. There are some other insight in it. So in this method, we need to introduce a law called the Kirchhoff current law. Create CHHOFF. CHHOFF, Kirchhoff. Should be something like this. This is difficult to spell because it's not an English name. Kirchhoff is a German. Kirchhoff voltage law. So in short, I usually call it KVL, and another law is called KCL. Kirchhoff current law. Kirchhoff current law. So with these two laws, you can apply to all the circuit, not only linear circuit but also non-linear circuit. Linear circuit is something like the RLC circuit. So as long as you know the KCL and KVL, you can actually solve, I can say, all the circuit. But in this page, we use the KVL, but in the textbook, it does not call it the KVL or KCL. But in circuit theory textbook, we usually call it KCL, KVL. Okay, so the battery is ideal. So the battery is ideal. The potential difference between the terminal is equal to E. So the voltage difference between A and this point is E. And when it passes through the battery to the high terminal potential, in this textbook, it assumed that the voltage at this point is VA. The voltage at this point is VA. But usually, we can arbitrarily assign a point, any node of a circuit to be ground. It's fine. You can assume this is a ground node, or assume this is a ground node is also okay. But not both. You can only assign only one node to be the ground node, which will not influence the answer, because as we know, we only care about the voltage difference. So we can arbitrarily assign any point of the circuit to be ground node. Some of them may be convenient for calculation. So usually we'll intentionally choose one rather than randomly pick one. But in the textbook, the argument is that as long as this voltage is VA, so VA is something like this. So when we're going through this loop from this point to this point, the voltage should be VA plus E. E is the voltage difference between the battery. And then try to go through the resistor, and then according to the Ohm's law, the voltage drop for the resistor should be IR, and this should be high, this should be low, so this is minus IR. And going back to this point, because the wire has no voltage drop, we usually assume the connection is has zero in resistance. And in circuit theory, we usually call it the lump circuit. Which means that we assume all the resistance usually is sufficiently small, and then we can group it into the resistor, and assume that the connection itself has a zero resistance. In this case, going back to the VA, so that this one should equal to VA, and VA can be cancelled. That's why we can just assume it to be a ground node, then VA is 0. And finally, we can get the same answer, I equals to E over R, which is a very trivial conclusion. It's nothing but an Ohm's law, I think. So, calculate the current in a single loop circuit. It used the loop rule, the algebraic sum of the change in potential encountered in complete traversal of any loop. Any loop circuit must be 0. And I usually call it not KCL, KVL, Kirchhoff voltage law. Kirchhoff voltage law. And then use the resistance rule. The voltage drop of the resistor is minus IR, or the voltage drop is IR. So the change in potential is minus IR. I think it's nothing but a Ohm's law. So the EMF rule is like from the negative terminal to the positive terminal of an ideal EMF device. The change in potential is plus E. So you only deal with some plus or minus sign, which is the easiest path for you to make mistakes. If you cannot deal with this positive negative sign, then you make mistakes. But after you get used to it, it will be very simple. So the next case is still single loop circuit, but the EMF device is not ideal. It has an internal resistance. So this graph is pretty nice demonstration. So we have VA at point A, VA at point A. So as we can consider a loop, so that we can consider a loop in this direction. It's just like it try to flatten this circuit into this way. A is here, E is here, and then resistor, internal resistor, small r, and then point B is here, R is here, and then go back to point A. So it is connecting like this. Well, this figure is pretty nice for you to get familiar with it. So the voltage, the electric potential at point A is VA. So going through this EMF, it go up by E, and then the current should be going clockwise because this is positive side, this is negative side. So the charge is supposed to going clockwise, which means that this small resistor will have a small voltage drop to VB at this point, and going to this point, this is ideal wire, so the voltage should be remain. And then going through this resistor, the voltage should drop by IR. This should drop by I, small r, I, capital R. And then going back to VA. So the voltage across this loop should be something like this. And according to KVL, the voltage change over a complete loop should be 0. Remember that the loop should be complete. And for figure A, so that a real battery with internal resistance R, Y to an external resistor, capital R. So figure B, so the graphical change in electric potential around the circuit. Now we apply the loop rule across the beginning. So we apply the KVL. So we will have E is positive, IR is negative, I capital R is also negative, and going for the whole loop, and then it should be equal to 0. So finally, I should be equals to E over R, capital R plus R in bracket, or something like this. Yeah, so actually E and R's are the known variable, and I is what we hope to find. As long as we know I, we can know the voltage of every point in the loop easily. So the next is the resistance in series. Actually, we're still applying the KVL. So we have, in this figure, we have E is positive, minus I R1, and minus I R2, and minus I R3 equals to 0. Also using the KVL. So that we have I equals to E over R1 plus R2 plus R3. Okay, so this is very simple. We just move them to the right hand side and then just factor I out and then derive it. And for this one, if we just we consider the equivalent resistance, which means that if we just remove these three resistance R1, R2, and R3 by a equivalent resistance. And then suppose we put them in a black box. Suppose we put this part into a black box and put this part into a black box. And what we can do is to change the voltage and then to test the current. If they are equivalent, it means that we cannot distinguish that these two cases. Then we will say that these two circuits are equivalent. If we have a voltage to be 0, the current will be 0. They are the same. If it is a EMF E, then the current will be something like this for all of them. And if it is 2E, then the current will be double. Then as long as we are varying the voltage source, then we can measure the same current. Then we'll say that they are equivalent. And in this case, for this circuit, also applying the KVL, we have E, this is E, and the voltage drop for the resistance is minus I Req. So that we have I equals E over Req. And as long as equivalent, these two currents should be the same, which means that R1 plus R2 plus R3 should be equals to Req. So for series resistance, we know that we add all the resistance together. Or in generally, if we have n resistor in series, we add all of them together. We have all of them together to be the equivalent resistance. So here is a simple summary. When a potential difference V is applied across the resistance connected in series, the resistance have identical current. It is a simple case of the KCL. The current should be the same. The current going into this terminal and going out should be the same. Going into this terminal and going out should be the same. The current cannot be stay in here or going out in a different path, because they are not actually one path. They are actually one path, and actually the charge cannot be stay in a resistor, so that the current within this loop should be the same. Should be the same. And this is a simple case of KCL. But generally I will talk about the KCL later, a bit later. So resistor connect in series can be replaced with Req, equivalent resistance, and it has the same current and the same voltage potential difference. And actually, you can just add all the resistance together to find the equivalent resistance. So next, potential difference. Potential difference is something like to find a potential difference between any 2 points in a circuit. Start at one point and traverse in the circuit to another point, followed by any path, and add algebraically the change in the potential you encounter, which means that you can actually find the potential difference between maybe this point and this point, or this point and this point, or maybe there are not so many points. Maybe no. there are only 1, 2, 3, 3 points, so there are not much case, not many case to raise, for example, to raise example. But actually, you can find the voltage difference between the small resistance R, something like that. Thus, the potential difference VB minus VA, VB minus VA is the terminal from voltage difference V across the battery is given by E minus IR, E minus IR. Because when you want to calculate the voltage difference between point B and point A, so you go from this point going upward. So this is E, and this is minus IR for the small resistor. So the voltage between VA and VB is this. And this should be VB minus VA, not VA minus VB. You should careful about the polarity. And actually, this should be equals to I capital R. This should be equals to I capital R. Because when you want to calculate the voltage difference of A and B, you can go in this way, you can go in this way, and the current is going this way, so the voltage drop should be, this point is high, this point is low, so it should be I capital R. So it mentioned about the grounding of a circuit. That's what I mentioned before. Grounding a circuit usually means connect one point in the circuit. One is very important. You cannot connect more than one, unless you really know that the voltage potential at that 2 points are actually the same at any situation. So connecting one point to ground, which means the voltage at that point is 0, actually equal to electric conductivity most of rock below the ground. Okay, so power of the EMF device, PEMF, is actually IE, the current times the voltage, or VI, IV, I times V, because for ideal case, it does not have intrinsic resistance. So the only possible expression is IE. I times E is the power dissipated by the battery. Power display of the battery. So let's consider a simple example. Okay, the EMF and the resistance in the current in the circuit of the figure have a following value: E1, E2, R1, R2, and R, capital R. What is the current I in the circuit? So in this example, let us consider a loop like this. We can simply follow the direction of the I given in this problem. Otherwise, you may feel confused. So actually, maybe we can start at this point, and going clockwise. So first, we go through the EMF1. because we're going clockwise. So this point is low, this one is high. So this is positive, and then going this way. And then E2, for E2, this one is high, this one is low, but we are going this way. So we should multiply by E2. And I is going clockwise, so going through I2 should be minus IR2. And then going to here, and then after going through R2, it's going to point C and point B. So this one should be minus I capital R. And then from point B to the original point, R1 should be minus IR1 equals to 0. So this is the simple case of KVL. So finally, we will get that I equals to E1 minus E2 over R1 plus R2 plus capital R. So we substitute the number 4.4 minus 2.1 over R1 is 2.3 plus 1.8 plus 5.5. So finally, the answer is 0.240 ampere. Okay, so this is pretty easy. So for part B, it's asking you about the potential difference between the terminal of battery 1, between the terminal 1, which means point B and point A is the terminal of battery 1 in the green box, in this green box. So usually we will calculate VA minus VB rather than VB minus VA, which is a positive value. So if we write VAB, which usually means VA minus VB, and it should be E1 minus IR1, and E1 is 4.4, I is 0.240, and multiply by 2.3. So VAB is 3.8 volt. So this is pretty easy. Yeah. And well, so let's